Hello everyone, thanks for coming. Today we're going to do a review of our week 7's lecture for the ODE course. So in this week, we talked about the Frobenius methods to get a series solution or a solution that has close relationship to a series for a second order ODE near a regular singular point. So for the regular singular points, we look at this equation with x equals to 0 as a regular singular point. Suppose xp and x squared q, they have the series expansion. In this form, we first solve the initial equation to get the two roots r1 and r2. Similar to solving the Euler's equation, we assume that the solution takes this form, xr times a series function. Note that for the Euler's equation, this whole series only has the lowest term 1, but as a more general case, the series may have infinitely many terms. In this sense, if we plug this back into this differential equation, we know the lowest order term, the coefficient in front of the lowest order term xr should be 0. So in the end, we can obtain a recurrence relation. We can obtain this recurrence relation that links an with a0 to an minus 1. In this way, we can determine the coefficients term by term, given that fr plus n does not equal to 0. Fr is defined here. So there are many subcases. For example, if the two roots, the difference between two roots is not a positive integer, then using the Frobenius methods, we can get two linearly independent solutions. Note that for the roots, for the larger root, we can always get one solution as xr1 times a series function. If the two solutions, if the two roots to the initial equation are the same, r1 equals to r2, then the other linearly independent solution should be the first one times ln x times xr1 times a series, where bn is the derivative for anr1 with respect to r. The third case, which is the most complicated one, is a case when r1 minus r2 equals to an integer. So in this case, the second solution is ay1 ln x times xr2 times a series solution, where those Cn, they are to be determined by this constant a. So in different scenarios, we indeed can formulate two linearly independent solutions for the general second order linear ODE. As a special case, we have the Bessel's equation. So the Bessel's equation is a very representative second order linear ODE which has a regular singular point at x equals to 0. So the initial equation is r squared minus nu squared. So the two roots are plus minus nu. We are interested in three cases: nu equals to 0, nu equals to 1/2, and nu equals to 1. If nu equals to 0, we know that the roots to the initial equation are repeated. In this case, we can get the Bessel's function of the first kind as a solution, and then the Bessel's function of the second kind. So h of m, this is defined as a summation from 1 to 1 over m. And the first term, j0 ln x, this is a second solution which is proportional to the Bessel function of the second kind of order 0. When nu equals to 1/2, we have the Bessel's function of the first kind and Bessel's function of the second kind, j1/2 and j minus 1/2. That is sin x divided by square root of x times a factor, and cosine x divided by square root of x times a factor. Finally, when nu equals to 1, The two roots also differ by a positive integer 2. So this is the first solution, the Bessel function of the first kind of order 1. And the second solution is minus j1 log x plus this whole bunch of stuff. So we can see that when nu equals to 1/2, the two solutions, linearly independent solutions, they take a very special form. But if that is not the case, then the second solution, the Bessel's function of the second kind, can be more complicated. So the general solution is the linear combination of the Bessel's function of the first kind and the Bessel's function of the second kind for x greater than 0. If x is smaller than 0, we can do a variable transformation. We can let Xi to be minus x and then solve for y on Xi. Thanks for listening.